Alright, let's go. Number 10. The Philadelphia Experiment. In October of 1943, at the Philadelphia Naval Shipyard, the United States Navy was working on a routine defensive problem. German magnetic mines had been sinking Allied shipping across the Atlantic, and the standard countermeasure was called degaussing, running electrical current through a ship's hull to cancel out its magnetic signature so the mines would not detonate. It was ordinary engineering. It is well documented. The physics of degaussing is understood and unspectacular. You reduce a hull's magnetism. That is the entire mechanism. Degaussing does nothing to visible light, nothing to radar reflection, nothing to the fabric of space-time. A degaussed ship remains fully visible on every wavelength the human eye and every 1943 sensor could detect. That was the prediction. That was also the outcome recorded in the Navy's own logs. Something else appeared instead. By the mid-1950s, letters were arriving at the desk of the astronomer Morris K. Jessup, signed by a man calling himself Carl Allen, claiming the Us Eldridge had turned invisible during those trials. Then teleported to Norfolk. Then reappeared with sailors fused into the steel. The letters came from Carlos Miguel Allende, and Jessup reproduced excerpts in his 1955 book, The Case for the UFO. The Office of Naval Research has issued formal denials of the incident since the early 1990s, and continues to publish a standing FAQ on the Navy's own website confirming that no such experiment occurred and no personnel were harmed. The ship's deck logs place the Eldridge elsewhere on the disputed dates. Every attempt to reconstruct a real event underneath the story has failed. Surviving crewmen interviewed in the 1990s described routine wartime patrol duty. No physicist has proposed a plausible mechanism by which mid-century degaussing hardware could bend light or displace mass through time. The tale has, nevertheless, outlived its debunking by more than 70 years, boosted first by Charles Berlitz and William Moore's 1979 book. Then by the 1984 feature film adaptation, then by every conspiracy channel that found the material too useful to fact-check. The interesting question is not whether the Eldridge disappeared. It did not. The interesting question is why a story built on one anonymous letter, contradicted by the ship's own paperwork, refuses to die. Some part of the culture wants at least one of these stories to be real and keeps voting to protect it. What does it say about a species that will trade a boring, verified archive for a single unverified letter and go on trading decade after decade? The next item was quieter, better organized, and for a specific afternoon in Massachusetts, designed as a real test. Number 9. The MIT Time Traveler Convention. In late 2004, a graduate student named Amal Durai was sitting in Cambridge working on a mundane problem in computer science and thinking, on the side, about a design flaw shared by every earlier attempt to prove or disprove time travel. Previous efforts had been informal, poorly publicized, and unreachable to any hypothetical future traveler. Durai's idea was to fix the advertising problem, then run the experiment as a party. The logic here is careful. A time traveler coming back from any future era needs two things: a working machine and a known destination, a specific location, and a specific moment they can aim for. If you publicize those coordinates widely enough and preserve them in enough long-lived archives. Then, in principle, any future civilization capable of building the device can plan the trip whenever the technology arrives, no matter how many centuries downstream that turns out to be. The event was scheduled for the 7th of May 2005 on the MIT campus at coordinates carried in advertisements placed in physical newspapers, on stone plaques, and in indexed archives specifically designed to survive. The convention was covered by the Boston Globe, by CNN, by Nature, and by essentially every major science outlet operating that year. Guests arrived. Some brought signs welcoming visitors from the future. One attendee wore a costume, another had prepared a paper on paradox resolution. The organizers had, seriously, prepared a landing zone. They had considered logistics that would sound absurd in any other context. How to receive a person arriving from 3,000 years ahead. Amal Dorai has since been interviewed by MIT's own alumni publications about the event and the reasoning behind it. Nobody came. That is the entire dataset. And the failure parade is where it gets uncomfortable, because there is more than one reading. The Traveler was impossible reading, time travel is never invented. The Traveler was uninterested reading, it is invented. But nobody bothered. The Traveler was forbidden reading, it is invented. But the future has rules against tourist trips into 2005. The Traveler was imprecise reading, the coordinates were published but not preserved in the right archives, and every future civilization that built a machine simply lost the address. Each of these explanations is unfalsifiable by the same event. What Dorai's convention actually demonstrated at human scale is that this is the best designed real-world test humanity has ever run for the existence of time travelers, and the result was silence. Every person who ever wondered whether the future is watching now has one data point. From an afternoon at MIT, and it is the data point of an empty room. Either the machine is never built, or every civilization that builds one has decided a college party is not worth the trip. Both readings say something. The next item is where the folklore ends and the peer-reviewed physics begins. Number 8. The faster-than-light neutrino anomaly. In September of 2011, physicists working on the Opera experiment at the Gran Sasso National Laboratory in Italy were doing what neutrino physicists do, measuring the time of flight of subatomic particles fired from a source hundreds of kilometers away. The source was CERN, in Switzerland. The particles were muon neutrinos. The distance was 730 kilometers of solid Earth. The measurement was routine, until the timing numbers came back wrong. Special relativity is not gentle on this. The speed of light in vacuum is the universe's rigid, non-negotiable cap on causal signaling. Anything that outruns it is not merely fast, it is mathematically equivalent to a signal moving backward in time, viewed from certain reference frames. The prediction, for a neutrino traveling 730 kilometers, is a very specific arrival time, and the tolerated deviation from that time is essentially zero. The neutrinos arrived early, 60 billionths of a second early. Consistently, the collaboration's spokesperson at the time was Antonio Ereditato, and the result was published to the RxIV in September 2011 under the title Measurement of the Neutrino Velocity with the Opera Detector. The paper listed roughly 170 co-authors. The number every commentator seized on was that 60 nanosecond lead over 730 kilometers, small in ordinary terms. Catastrophic in physics. What followed is the retention engine of the entire story, because the physics community did not dismiss the result. The Minos collaboration at Fermilab began preparing an independent measurement. The Icarus collaboration, also at Gran Sasso, ran a parallel analysis and reported in 2012 that their neutrinos arrived exactly on time. Systematic effects were audited. GPS synchronization was re-examined. Cable connectors were checked. A group at Imperial College London and separately several theorists at Princeton wrote out what the theoretical consequences would be if the number held. Nobody said the number could not hold. They said, formally, that if it did, causality itself was compromised. And they meant it. In February of 2012, the Opera team announced they had traced the anomaly to a fiber optic connector between an external GPS receiver and a computer. The cable had not been fully screwed in. The apparent superluminal effect vanished. Ereditato resigned as spokesperson later that year. For 6 months, some of the most rigorous experimentalists alive did not know whether the universe permitted the past to reach the present. They took causality violations seriously because the data compelled it, and only stopped taking it seriously when a hardware fault explained everything. If the physics community had cut corners and dismissed the reading, we would remember it as a scandal. Because they didn't, we remember it as a system working correctly. But for those 6 months, none of them knew that yet. The next item is where a government agency decided to fund the question directly. Number 7. NASA's Breakthrough Propulsion Physics Program. In 1996, an aerospace engineer named Mark Millis, working out of NASA's Lewis Research Center in Cleveland, put together a proposal for something the agency had not previously funded on record: a formal research initiative into speculative propulsion physics that were not proven, not built, and not disproven either. The mandate was narrow and honest: identify what general relativity and quantum field theory permit but no engineer has attempted, and evaluate whether any of it can be moved from the equations onto a lab bench. The prevailing assumption at NASA in the mid-1990s was that propulsion research meant chemical rockets, ion engines, and, at the extreme end of speculation, nuclear thermal designs. Anything involving space-time engineering, Alcubierre metrics, wormholes, closed Timelike curves was philosophy. The Breakthrough Propulsion Physics Program, as it was formally named, changed that classification. It became a real budget line item. For 6 years, from 1996 through 2002, the program funded workshops, peer-reviewed studies, and contract analyses. It was small, roughly $6 million total across its lifetime, a rounding error in NASA's budget, but it was real. The theorists it engaged included Harold Puthoff, whose polarizable vacuum model treated empty space itself as an engineerable medium in which the local speed of light and, by extension, the local flow of time could in principle be modulated. Papers from the program were archived and are still accessible through NASA's Technical Reports Server. Millis has subsequently co-edited an academic volume, Frontiers of Propulsion Science, published by the American Institute of Aeronautics and Astronautics in 2009, summarizing what the program actually concluded. What it concluded was, in the plainest reading, that the physics required for warp drives, wormholes, and closed Timelike curves is not forbidden by known laws, only monstrously impractical. Every candidate mechanism reviewed required energy densities, exotic matter, or geometrical precision that no known engineering path could produce. Some required negative energy densities, allowed by quantum field theory in vanishingly small quantities, but not in the amounts a working device would demand. Others required objects of infinite length. None of them collapsed under mathematical scrutiny. All of them collapsed under engineering scrutiny. The program was discontinued in 2002. The stated reason was budget priorities, but the substantive reason, visible in the papers themselves, was that 6 years of theoretical work had produced no engineering path forward. For a scientist, that is the difference between failure and defeat. Failure is when the equations forbid you. Defeat is when the equations permit you and the machine shop cannot follow. In that field, being defeated is not the same thing as being wrong. And NASA quietly closed the program without ever telling the taxpayers which one it was. The next item took that same institution one generation further and put actual hardware on a bench. Number 6. NASA Eagleworks and the Warp Field Interferometer. Sometime around 2010, a physicist at NASA's Johnson Space Center in Houston began setting up an experiment that his colleagues privately doubted would ever be publicly acknowledged. His name was Harold Sonny White, and his idea was to take Miguel Alcubierre's 1994 warp drive metric, a solution to Einstein's field equations that permits faster-than-light travel by warping space-time around a bubble containing a stationary ship, and ask whether the warping itself, at microscopic scales, could be detected in a laboratory. The theoretical prediction is precise. The Alcubierre metric, and by extension every closely related solution that produces closed Timelike curves, requires space-time to distort in a specific mathematical shape. If such distortion could be produced at any scale, even a subatomic one, it should register on an interferometer, the same instrument family used to detect gravitational waves. If it cannot be produced, the interferometer sees flat space-time and nothing else. White's rig used a laser-based interferometer designed for extreme sensitivity, and preliminary runs, reported in a 2013 conference paper for the American Institute of Physics, showed small positive signals, apparent path length differences consistent with what a microscopic warp field would produce. The paper's careful phrasing was, "The results are inconclusive," and White himself did not claim a working warp field. He claimed a detector that had produced readings the team could not immediately explain. The signals were near the noise floor. The energies involved were tiny. The setup had been reviewed by a NASA advisory board. The failure parade arrived within months. Independent physicists at other institutions examined the experimental design and identified multiple systematic issues that could produce the reported signal without any space-time distortion at all. Thermal drift in the interferometer's optical mounts, air currents from the room's ventilation, vibration coupling through the isolation table. When later runs corrected for these effects, the signal shrank towards zero. A 2016 review paper co-authored by White himself acknowledged that the readings were consistent with instrument noise. Eagleworks continued operating on other projects, but never reported a positive warp field measurement again. For a short window, though, inside a NASA laboratory paid for by a real budget, a graph looked like it might be showing microscopic space-time distortion. The graph turned out to be showing the room's air conditioning. That is not a failure of ambition. That is what the process is supposed to catch, and it caught it. The equipment existed. The government paid for it. And for a brief, uneasy moment, the readout on a screen at Johnson Space Center suggested, incorrectly. In the end, that a lab-scale warp field might have registered on an instrument. The next item did not need any hardware at all. It only needed the universe to have already left the raw material lying around. Number 5. J. Richard Gott's Cosmic String Time Machine. In 1991, a Princeton astrophysicist named J. Richard Gott was working on cosmic strings, hypothetical. One-dimensional topological defects that some theories predicted should have been left behind by phase transitions in the first fractions of a second after the Big Bang. Cosmic strings, if they exist, are exotic in the extreme, ultra-dense, effectively infinite in length, and capable of warping space-time around them the way a mass warps it, but in a strange two-dimensional conical geometry. The standard result at the time was that closed Timelike curves, the mathematical objects that permit backward time travel, required either exotic matter with negative energy density or infinite constructions like Frank Tipler's rotating cylinder, which needed a rotating object of infinite length rotating at half the speed of light. Neither was buildable. Both were considered mathematical curiosities. That was the accepted position. Gott's paper, published in Physical Review Letters in 1991 under the title Closed Time-like Curves Resulting from Pairs of Moving Cosmic Strings, changed the accepted position. He showed that two cosmic strings, passing each other at speeds close to the speed of light, would warp the space-time around the crossing point into a genuine closed loop in time. Not a metaphor. A solution to Einstein's field equations. The elegance of it is that Gott's construction did not require humanity to build anything. Cosmic strings, if they exist, are relics, objects the early universe may have already produced, still drifting somewhere in the cosmos, waiting to be found. The engineering problem collapsed into a search problem. Stephen Hawking objected almost immediately. In a 1992 paper introducing what he called the chronology protection conjecture, Hawking argued that closed time-like curves would inevitably be destroyed by quantum vacuum fluctuations before they could function, that the universe in effect was self-correcting against time machines. Later analyses, by Gott himself and by Kurt Cutler, refined the mathematics without resolving the disagreement. A separate calculation showed that assembling the required cosmic string energy density from ordinary matter would demand more mass energy than the observable universe contains. But a natural pair, already produced by the early universe, would not need to be built. The failure here is a failure of confirmation, not of theory. No telescope has ever detected a cosmic string. Searches for their gravitational lensing signatures have come up empty. The 2015 detection of gravitational waves opened a new channel for searching, and that channel has, so far, also been quiet. If humanity is ever going to find one, it will be through survey data, not construction blueprints. Somewhere in the sky, at a resolution nobody has yet reached, the crossing may or may not be waiting. Nobody has ever confirmed a cosmic string exists. But the mathematics is clear, if even one pair has ever crossed under the right conditions anywhere in the observable universe. A working time machine has already occurred, without anyone building it. The next item removed the last excuse the previous three had leaned on. Number 4. Amos Ori's vacuum time machine. In 2005, an Israeli physicist named Amos Ori at the Technion, Israel Institute of Technology, was working on a problem that had frustrated every serious time machine proposal to that point. Every earlier solution to Einstein's field equations that permitted closed Timelike curves had required something exotic. Tipler needed infinite length. Gott needed cosmic strings. Wormhole models required negative energy densities, allowed by quantum field theory only in vanishing quantities. Ori was asking whether space-time could be made to loop back on itself using only ingredients the universe demonstrably contains. The prevailing view held that this was impossible. Kip Thorne and colleagues had shown in the late 1980s that traversable wormholes required exotic matter. Every alternative construction seemed to demand a substance physics could describe on paper, but had never observed in nature. The consensus was that the time machine problem was, at minimum, a matter supply problem. Ori published in Physical Review Letters in July of 2005 under the title A Class of Time Machine Solutions with a Compact Vacuum Core. He showed that space-time could, in principle, be curved into a closed loop within a finite, bounded region, using only vacuum and ordinary matter, no exotic ingredients required, provided the geometry was arranged with sufficient precision. The specific mechanism in Ori's model is subtle. A donut-shaped region of curved empty space, surrounded by an envelope of ordinary matter, would act as the time machine. The vacuum core itself contains no exotic energy density. The curvature is generated by the arrangement of the surrounding matter. The mathematics was reviewed, published in one of physics' most rigorous journals, and over the 2 decades since has not been refuted on its own terms. Later analyses, by Ori and collaborators. An independent commentary from Kip Thorne have identified concerns about stability and initial conditions, but no fatal error in the underlying construction. The failure parade is where it gets uncomfortable. The stability question is real. Small perturbations in the initial arrangement may cause the geometry to collapse before the loop closes. The initial conditions question is real. No known process in the observed universe would naturally produce the required arrangement, meaning a civilization would have to engineer it. The energy densities involved, though not exotic, are astronomical, well beyond current or foreseeable technology. Some critics, including Hawking in later writings, have argued that quantum effects would destabilize Ori's construction before it could function, echoing his 1992 chronology protection argument. The point remains. For the first time, the missing ingredient stopped being an undiscovered particle. It became engineering precision at a scale humanity does not possess yet, a very different and much more solvable category of impossible. The next item was recent enough that it made news, and specific enough that it tested one of the exact loopholes people had been hoping for. Number 3. CERN's alpha-G antimatter gravity experiment. In September of 2023, physicists working on the alpha-G experiment at CERN in Geneva completed what had been considered, for decades, one of the most technically difficult measurements in modern physics: how antimatter responds to gravity. The team, led by Jeffrey Hangst, had spent years learning to trap antihydrogen atoms, cool them, and hold them in a magnetic bottle long enough to run a controlled release. The reason the measurement mattered, and the reason it belongs on this list, comes from the way physicists actually describe antimatter mathematically. The Feynman-Stickelberg interpretation, developed by Richard Feynman and Ernst Stickelberg in the mid-20th century and used routinely in modern particle physics, treats a positron, the antimatter counterpart of an electron, as mathematically identical to an electron traveling backward in time. This is not a metaphor. It is the formalism used in the Feynman diagrams every graduate physics student learns. If that formalism is taken at face value, then measuring how antimatter falls under gravity is, in a specific mathematical sense, the first direct experimental test of how time-reversed matter behaves in a gravitational field. The alpha-G result was published in Nature on the 27th of September 2023. Trapped antihydrogen atoms were released inside a vertical magnetic trap. The direction they drifted was measured. The result, to a precision sufficient to rule out anti-gravity effects, was that antimatter falls downward, exactly as ordinary matter does. The measurement was consistent with Einstein's equivalence principle to within the experiment's tolerance. The failure parade here is a failure of exotic loopholes. Some theorists had proposed since the 1950s that antimatter might fall upward, that the negative gravitational coupling would explain both the matter-antimatter asymmetry of the universe and open exotic possibilities for time reversal physics. The measurement closed off that possibility. Other proposals had suggested antimatter might have a gravitational coupling different in magnitude but not in sign. Alpha G constrained those as well, though with less precision. The straightforward reading: antimatter is not gravitationally distinct from matter, held, what the result cost and what it saved are worth separating. It cost the exotic gravitational loophole that a certain kind of time machine proposal had leaned on. It saved the equivalence principle, and by extension the coherence of general relativity as physicists have understood it for a century. For one afternoon in Geneva, a team of physicists dropped time-reversed matter and watched to see if it would fall the wrong way. It did not. But the fact that this was a real, fundable, peer-reviewed question in 2023 at the world's most credentialed lab tells you exactly how seriously backward time matter is still being taken. The next item was smaller, older, and, measured in what it actually demonstrated, closer to the target than anything that came before it. Number 2. The University of Queensland's simulated time travel experiment. In 2014, two physicists at the University of Queensland in Brisbane, Martin Ringbauer, then a PhD student, and Timothy Ralph, his supervisor, were working on quantum optics, the branch of physics that manipulates individual photons. They were interested in a paper the theoretical physicist David Deutsch had published in 1991 in a journal called Physical Review D, titled Quantum Mechanics Near Closed Timelike Curves. Deutsch had argued that if quantum particles could travel through closed timelike curves, the resulting behavior would be self-consistent, meaning paradoxes like the grandfather paradox would automatically resolve rather than break physics. The mainstream view at the time was that Deutsch's model was elegant but essentially untestable, because nobody could produce a real closed timelike curve to send a particle through. The prediction was locked away behind the impossibility of building the thing that would test it. That was the accepted state of affairs. The Queensland team found a route around the impossibility. Using quantum entanglement, they engineered a two-photon system in which one photon behaved mathematically identically to a particle that had traveled through a closed time-like curve without any particle actually leaving the present moment. The paper, Experimental Simulation of Closed Time-like Curves, was published in Nature Communications in June 2014, with Ringbauer as lead author. The result? The photons behaved precisely as Deutsch's 1991 equations predicted. Self-consistent. No paradoxes. No contradictions in the measurements. The team confirmed a decades-old theoretical prediction about how time-traveling quantum particles would behave, using photons that never traveled in time. The failure parade here is a parade of interpretive disagreements rather than experimental failures. Some physicists argued the analog was too loose, that entangled photons cannot substitute for a genuine closed time-like curve because the physical mechanism is different, even if the mathematics coincides. Others pointed out that Deutsch's model itself is one of several competing quantum mechanical treatments of time travel and rival models by Seth Lloyd and collaborators, published in Physical Review Letters in 2011, predict subtly different behavior that the Ringbauer-Ralph setup could not distinguish. And a persistent objection, made by several theorists, is that a simulation of the mathematics is not evidence that the physical situation can occur, only that if it occurred, it would behave as predicted. No photon left the present moment. But for the first time in the history of the field, a real laboratory-produced data that matched, number for number, what a working time machine's paradox-resolving physics would look like, the closest thing anyone has ever generated to hard experimental evidence that the mathematics of time travel actually functions. If the mathematics functions. And if reality tracks the mathematics closely enough elsewhere, the question of what still separates the simulation from the thing itself becomes uncomfortable to answer. The final item is where that discomfort came out from behind the equations and hit the front page of every newspaper in the world. Number 1. The Google Caltech Quantum Wormhole Experiment. In November of 2022, a team led by Maria Spyropoulou at the California Institute of Technology, working with collaborators at Google, Harvard, MIT, and Fermilab, published a paper in Nature that produced one of the most misreported science stories of the decade. The title of the paper was Traversable Wormhole Dynamics on a Quantum Processor. The headlines that followed said simply that physicists had built a wormhole. The theoretical framework the experiment tested is called ER_EPR, a conjecture published in 2013 by Juan Maldacena of the Institute for Advanced Study in Princeton and Leonard Susskind of Stanford. Maldacena and Susskind proposed that two seemingly unrelated pieces of theoretical physics, Einstein, Rosen bridges, which are the mathematical structures Einstein and Nathan Rosen described in 1935 that later came to be called wormholes, and Einstein-Podolsky-Rosen entanglement, the quantum correlation between separated particles Einstein and colleagues described in the same year, might in fact describe the same physical object viewed from two different theoretical vantage points. If ER/EPR holds, then two entangled particles are, in some deep sense, connected by a wormhole. The Spyropoulou team took that conjecture and ran it on Google's Sycamore quantum processor. They configured 9 qubits to implement a simplified holographic model called the Sokdev-Ye-Kitaev model, engineered an entangled state between two systems within the processor, and observed information transfer that matched quantitatively the predictions of a traversable wormhole in the SYK framework. The information moved through the quantum circuit in the specific pattern a wormhole would produce. The failure parade began the moment the paper appeared. Peter Woit, a Columbia mathematician and long-standing critic of speculative theoretical physics, wrote publicly that no wormhole had been created, that the experiment had simulated the equations of a wormhole on a quantum computer, no more. The Nature paper's own authors, when pressed, described the result as a wormhole-like experiment and a quantum system that has the same properties as a wormhole, not a physical hole in spacetime. Adam Brown, one of the co-authors, gave interviews clarifying that no spacetime had been bent. Several theoretical physicists argued the SYK model used was too small and too simplified to be considered a rigorous holographic dual of a real wormhole. Others accepted the framework but disputed whether the ER/EPR conjecture itself is well enough established to justify the interpretation. Nobody opened a hole in spacetime that afternoon in California, but somewhere inside a chip cooled to a fraction of a degree above absolute zero, information moved through a mathematical structure that is, according to the leading theoretical framework in modern physics, the same object as a wormhole, described in a different language. If ER really does equal EPR, the distinction between simulated and real may not be as solid as the headline correction implied. And that is the disturbing possibility physicists are still, quietly, arguing about in seminar rooms. Every experiment on this list sits in the same uncomfortable place. Not one of them produced a working time machine. Every one of them was serious, funded, published, or in the folkloric cases, taken seriously enough by the culture to survive its own debunking for decades. What connects them is not a failure of imagination or a failure of science. It is that the mathematics of time travel is not obviously forbidden by the physics we know. And the boundary between the equations permit this and an engineer can build this turns out to be the actual location where reality is still being negotiated. The universe is not confused about whether time machines are possible. We are. If you want to see more videos like this, click the video on screen now.